Good afternoon, everyone. Welcome to Tah Poe Seminar Series 53 and talk number 2. And today our speaker is Dr. Sikarin Yoo-Kong, and today he will tell us about the q-deformed feature matrix. Okay, please welcome the speaker.
And then, is that okay now? Okay. So I have to start over again. do I have to do that? No. Well, I continue then. Okay. So after Atom finished this work with me, and then he realized that actually physics may is not my his thing. Then he becomes bartender. Yeah. Actually, okay. Anyway, so and then the work get published in journal reports on mathematical physics. Okay. So, and this is all what I'm going to say today. So first, I'm going to give you a standard notion of Q deformation or Q analog. And then I'm going to talk about one parameter, Hamiltonian, Lagrangian, and entropies, as well as Kullback-Leibler divergence, okay? Something about entropy, this kind of thing. And then I give you a motivation, and after that, the motivation is something to do, the reason why we need to build up this kind of one parameter feature matrix, right? And then I give you a one parameter feature information as well as the feature matrix. And then we will discuss about this new version of feature matrix with a concrete example, normal distribution. And then I give you a conclusion, okay? So, okay, let's start with the question, what is a Q deformation or Q analog here? Well, I just get it from the Wikipedia, okay? Very simple. In mathematics, so if you get a standard theorem, like a standard derivative, right? And then you try to extend that notion by put a parameter in it, and then when you take an appropriate limit, you get the standard theorem back. That kind of, say, that Q analog or Q deformation in this context, okay? And well, you can find more information about history about building up this kind of Q deformation or Q analog on the Google. Yeah, please Google if you want to know more, okay? And so let's go to this some basic relation about Q analog. Okay, let's start with a non-negative integer n. We can rewrite in this way. With this limit, you get this n back. Then with this relation, you can construct Q, what they call Q number, actually here. With this Q number, you can also construct what they call Q factorial, okay? And then with this Q factorial, you also can construct the q exponential here, okay, which I do this kind of in the label here to be not the standard exponential function, but the q1, and then with the appropriate limit q approach to 1, and you get the standard exponential back. And then we also have the q analog of the logarithm function this way, okay, and then again with the appropriate limit, you get the standard logarithm back, okay. From this, so we also have a definition of q summation, q different, q product, and q ratio, like this one, like this, and then from all of this you can construct also the relation of the logarithm function, exponential function in this way. Well, a lot of things you can do, and then from this you also can define what they call q derivatives, okay, here in this. There are two types of q derivative. The first one, this one, and the first one that comes with the tutor. The difference is that the first one, in the denominator, you have like a q difference, something like that here. That is the thing. And then there is a relation between these two derivatives here. Okay, and then there is also a product rule, right, of this q derivative, okay, which is actually quite long, right? Anyway, okay, so this is all the basic that we need for the q analog relation, and then, well, let's move to the next topic about one parameter Hamiltonian and Lagrangian, which actually this is like the work that I did with my former master student at KMUTT, right? This guy, and then we can use a technique that called inverse calculus of variation. We can solve actually the Euler-Lagrange equation, and then we get a new type of Lagrangian that come actually with the parameter here, we call lambda here. And once we get this Lagrangian, we can use the Lagrange transformation to get this Hamiltonian, this one. Of course, this is for 1 degree of freedom, for simplicity. And then under the appropriate limit, we get the standard Hamiltonian and the Lagrangian back, okay? And so, well, if now I rewrite Hamiltonian a little bit by define this delta to be minus m lambda square here, and further on I redefine again this delta to be 1 minus q. Now my Hamiltonian can be rewritten in this way, okay? And there is some interesting feature is that if we now have to separate the system, right, like if you want to consider the total Hamiltonian, it just add them up like this way, right? But with this new kind of Hamiltonian, if you have two separate systems, when you add them up, you will get the extra term like this, right? This is what we have, and then you will see this kind of feature, a similar feature like this in the entropy context. Okay. Now we come to the entropy context. Okay, so we start with the first entropy that we call Lenji entropy, which is actually can consider that like a one parameter extant version of Shannon one. With the appropriate limit, you get the Shannon entropy back here, right? And then the key property of this Lenji is that if you have two separate systems, the plot system, the plot is just the product, right? The joint plot is just the product, and then the Lenji has like a additive property. That's what we have here. And so let's look at this note. If we have this kind of generating function here, you can get the Shannon entropy by doing this kind of derivative, and you take x equal to 1 later. Okay, that is the thing. Okay, remember, keep in your mind actually this one parameter version of this Shannon entropy, or we call Lenji, is additive process additive property. The next one, the next entropy is called solid entropy. And again, with this appropriate limit, we get the standard Shannon entropy back. And there is a relation between solid entropy and Lenji entropy. If you could solve for this summation of PQ here, and then you can put your solid entropy in terms of the Lenji entropy, like this one. And if you look at this carefully, it looks pretty much the same of what I have for this Hamiltonian here, right? It takes exactly the same form. And of course, then we know that actually this solid entropy possesses non-additivity, right? If you have two separate pop model, then you get this extra term like those in case of Hamiltonian that I mentioned. And furthermore, if we, well, actually we can express this solid entropy in terms of Q logarithm here in this way. It means that you have this kind of, when you can put thing in this way, it means that you have the average of this minus log Q pi. Normally, pi is nothing but in the context of, but this is, you get some extra parameter, right? Anyway, and then again, this is a very interesting feature. With this, the same generating function, we find that this solid entropy can be obtained by looking at this minus Q derivative of this generating function, right? Okay, so you get that, okay? And so now this is our one parameter entropy, okay? Next is the two parameter entropy that called Cramér-Rao entropy, okay? So we have R and Q as parameters in this context, and then if you take R equal to 1, you get Lenji back, and then if you take R equal to Q, you get solid entropy back, right? And then again, this two parameter entropy process non-additivity. This because we have this kind of extra term for like two separate pop system, okay? Anyway, now we come to a new object that we call Kullback-Leibler divergence. Okay, suppose that we have like a probability manifold, right? And we have two pop distribution that I call P and Q. And if you want to tell the difference between this P and Q, you can use this DKL. Okay, I will call this Kullback-Leibler divergence as a KL. This kind of object, you can use this one as a measure of how much difference between this P and Q on that plot manifold. Okay. And the first one is for the discrete case, and the second one for the continuous case, right? Okay. And so, well, but if you look at this formula here, actually, you see that actually the way that we construct this DKL actually based on definition of the Boltzmann-Gibbs Shannon entropy, right? Because it's the P log P something, right? Okay. And in the case of actually these 2 points is very close to each other, we can consider this Q to be like a P plus some little thing, right? And then you put back into this DKL, and then you do the Taylor expansion, and you keep only the first term of the expansion, you will get this quantity, which now I define, or I will call this one as a feature information, and I will explain later what is a feature information. But keep in your mind again is that you can get the feature information from the DKL or the Kullback-Leibler divergence. Okay. And there is a note here, since, well, this Kullback-Leibler divergence is not symmetric, then you cannot use it as a distance measure, right? Because it's not symmetric, then yeah, anyway, that kind of thing. Okay, so now we would like to generalize this Kullback-Leibler divergence. So there is many ways to generalize this, but this is one of them. Okay, so let's start with this very weird identity here. They call effective prop here. Okay, and they also introduce this kind of new kind of entropy, the average of this piezo over the Q here in this way that they define. And then they also define what they call fractional entropy here. And then with these two, they combine these two definitions. They get the two parameter Boltzmann-Gibbs Shannon entropy in this way. There are two parameters here, Q and Q prime. And then if you take Q and Q prime appropriately, well, approaching to one, you get the standard Gibbs-Boltzmann and Shannon entropy back. Okay, and then from this definition of two parameter entropy here, we can use this one to construct this Kullback-Leibler divergence. Okay, so you will have this one for two parameter, and this is for the discrete case, and then this is for the continuous case. All right, and then again, if these 2 points, the P and Q on the plot manifold is very close to each other, we can do this kind of thing, and then we do Taylor expansion, and then we keep all for the first term in expansion, you will get this two parameter feature information here. You see that there's two parameter Q and Q prime here. Okay, all right. Okay, so now I get this picture from the internet. Actually, this guy Frank Nielsen, I think, this very nice taxonomy on this kind of thing here. So on the top we have the standard definition of the entropy, right? Like a Gibbs Boltzmann entropy, and we have Shannon here. And then as I extend to you guys, you can extend the definition of entropy to get one parameter that we call Lenji, right? But this Lenji possesses the additivity property. Okay, and the other one is solid entropy, and also two parameter Sharma-Mitchell here, and these two possess non-additivity. Okay, because okay. Then, or you can look on this right-hand side. Actually, and what I mean by this arrow means that under appropriate limit on the parameter Q, you will get this standard entropy back. Okay. All right. So now we see that actually we can extend the definition or the definition of entropies to be like this one and this one. And then if you look carefully on this taxonomy, we also have another quantity that we call feature information, right? Then here, so the question is that is it possible to construct like a one parameter feature information here, right? And yes, there are also feature information and also feature matrix here. Then I'm going to explain to you guys later what is it about. Okay, this is the kind of very naive motivation that we have. Okay. Okay. So what is a feature? What is a feature information? If I would like to explain in a cartoon way, I give you this robot, okay? And this robot, well, if you look inside the robot, there is some tiny pieces actually working inside the robot, right? That you can look at. If you know that actually, if you can probe inside this robot and you know precise exactly what the configuration of this is, of the pieces, this, right? And then you know how this robot works. right? In globally, right? In global view, there's the way that robot work or moving the arm, moving the legs, that called entropy. That's the kind of thing. This is kind of analogy that I would have. Okay, so let's put in this way. So the feature information, we can use this guy to estimate the parameter in your plot model. All right, let's see the example. So this is a normal distribution, right? Okay, let's see that this curve, like you can see this curve is nothing like a robot actually, but the parameter here that actually control the behavior or the shape of the curve, that actually the mu and the sigma here is a parameter in this system. You can compare this mu and sigma as a tiny pieces that actually contain inside the robot. And then once you change this mu and sigma, the shape of the normal distribution change, something like that. Okay, and so the role of the feature information is to estimate this parameter in your system. That is the thing. Okay, so now I give you now the definition of the feature information. Actually, this guy is called log likelihood here. But actually, you can treat this out thing as a plot distribution, which actually for this one is come with parameter that we would like to estimate. Okay, this is the standard definition. Okay, but in the case that we have many parameters in the system, like a normal distribution, we have two parameters. We're going to have that we call a Fisher-Rao matrix here. The definition is given in this way. I'm not going to give you the derivation of the standard Fisher and the Fisher-Rao, but I just give you right away the formulation. And so again, so we get back to the Kullback-Leibler divergence in this situation on the plot manifold. So now in this situation, we have two different set of estimating parameters, theta and theta prime. And then we put these two pop distribution into DKL. And then we expand this theta around this theta prime around this theta. And then we keep on the first order term, you get the definition of the Fisher-Rao matrix. Again, what I would like to point is that there is a connection between Kullback-Leibler divergence and the Fisher matrix. That is the thing. Okay. And so there is a bound because the Fisher information is used to estimate the parameter in your system, right? There must be a bound. How good is it that you can use it to estimate the parameter? And then this is the way that we can construct the bound. It's called Cramér-Rao inequality. I don't know. I might pronounce the name wrong. I don't know. Is that called Cramér-Rao? I don't know.
Yeah, people just say Cramér-Rao.
Cramér-Rao. Okay. Cramér-Rao. Yeah. Okay. Cramér-Rao inequality. So we start with this kind of avalanche of this we call point estimator, and this is the parameter that we would like to estimate actually equal to 0, right, from this definition. And so, well, you can think that actually this parameter is kind of the fluctuation around the average point, right? And on the average, the fluctuation around that point is 0, right? And so we look at the first derivative of this this quantity, you will get these two terms. And with the definition of the plot, as I mentioned, that you can think this is nothing but the plot distribution. Like the definition of the plot, the whole thing is nothing but equal to 1, right? You get 1 here, and then once you get here, this side you get 0, you will get this relation, and you actually these two brackets coming from this one term here. You can split this this one into this bracket, okay? Okay. And once you get this, you're going to apply Cauchy-Schwarz inequality. you will get this kind of relation, and then you get that actually this is a bound for the feature metric, the inverse of the variance of your estimating parameter. That is the thing. Okay. And so furthermore, if in the case that you have the independent plot system, then you can write your feature metric in this way. Okay, the first term, then the second term, but the first, actually this coming from actually which one? This guy, I think this one, right? This is a feature, right? Yeah. If you treat this as if you treat this L as a plot distribution, you will get this one. And so since they are separable, and then you see that actually the derivative of the integrate of the plot must be zero, right? Because the sum of the plot must be 1, or the integrate of the plot must be 1, right? Then the first term is just vanished, right? Vanished, and then you get this only the second term here. And we see that actually the standard feature metric process the additivity property, right? Additive property, that is the thing. Okay. Okay. So now come to the crucial point. So this is a way that we're going to extend or to construct one parameter feature information. So there is a connection between action functional and the feature information. So in the case of one parameter here, we're going to have this feature information, and so we can redefine the parameter, this I call y in this way, and then the plot going to be put in terms of the y variable, and now this whole thing can be rewritten in this way, right? And then again, if you redefine the variable in this way, like you say that actually you have a new variable that you call q, actually nothing but the square root of the plot. Okay, you will get this one, and this is a new form. After you do some redefine variable appropriately, you will get this one. And then if you look at this one carefully, you can think that actually this is because we have the q times square. This is nothing like, if you think that y is nothing but the time variable, this term is nothing but the kinetic energy here, right? Then you can think that this is the I is nothing but the action functional, and the term inside the integration is nothing but the Lagrangian of the system. And with this Lagrangian, you can get the second order differential equation, which is nothing but equation of motion. It means, so with this, you can say that with the absence of interaction, the equation of motion in physics, for like a free particle, can be a result of extremizing feature information in this way. So somehow, we have the connection, I don't know, between classical mechanics and the information theory through this kind of connection. Okay, and so once we have action and we have Lagrangian, so let me get back to the work that I did with my student. Where is it? Here. Now, I'm going to use this kind of Lagrangian to build up a new feature information here. Since there is no potential, then there is no V here. There is only the kinetic term. So, sorry, a long way back. And so we propose here a new type of feature information in this way, and a new type of Lagrangian here. And then under the appropriate limit for this situation, we take lambda approach to 0. You get the standard feature back. Okay, and then it's not difficult to see that actually this Lagrangian going to give us exactly the same this equation of motion here. That's what we have. And so the thing is that if we expand this feature information with this one parameter with respect to lambda here, we will get what I call the hierarchy of the feature information. And the first one in the hierarchy is nothing but the standard feature information. And for the second one and the third one is they are no longer called feature information, should be something else yeah. And then this is the second term look like, which it look very weird, but well, if you look at this carefully, it's not in the standard form. What I mean by the standard form is not in the way that we say that this is the average of some quantity, right? What we did is that we redefine again the parameter as a P2 here as a P square. As we do this, we can put this I2 in terms of this thing. Then we can say that actually the second feature is the average of this whole thing, right? If we define this in this way, so we can do the same for the further function in the hierarchy, and we get this one, okay? And then we get this feature information in the summation in the infinite series here. Anyway. So now I recall two parameter feature information that we get from generalized Kullback-Leibler divergence, right? Actually, this A and B is nothing but this. There's something to do with Q and Q palm, right? And then we find that with the appropriate choice of this Q and Q palm, this two parameter feature information can be perfectly matched of what we have in this hierarchy, okay? That's what we have, right, in this table. If you choose this parameter carefully, you will get you can compare, right? And so next we're going to extend also Cramér-Rao inequality. The way we extend is that so normally the standard Cramér-Rao is you come with the normal p, right? But now the extension version is come with the p to the power q here, right? And then we do the same trick. We do the derivative with the theta, and then we get this in equation, and the QQ, well, the big Q is defined this way. Normally it should be 1 if this small q is 1. This is nothing but a standard clock definition, right? But well, for this situation, Q can be any number, right? Then we just keep it in this way, and then we have a J term in this way. And so now we're going to consider the J term here. We're going, well, once we have these two brackets here, we're going to apply that they call the Holder inequality. And we get this inequality inequality here, and also of course we get this equation, but with this constraint, okay, 1 over alpha plus 1 over beta must equal to 1, and then this is the range of the alpha and the beta here. And well, in this context, well, they call Q is as a solids index. I'm going to explain why they call solids index later. Okay, once you get this J, you will get this inequality here, and we say that actually this is extended Cramér-Rao inequality for this feature, one parameter feature information. And again, if you choose this order constant appropriately, like for this one, you will get the standard Cramér-Rao back, right? And then if in the case that you choose alpha to be 4 and this beta to be 4 over 3, and then this Q to be 5 over 4, you get the second one for the second one in the hierarchy here. And then you can keep going this way in like I put in this table here. Okay. So well, this is like the bound for each of the function in the hierarchy. That's the thing. Okay. So what I want to say is that this new kind of function is not additive. If we have two random two system of two model of plot that actually separate, okay, and then the plot is just nothing but the product of the plot, right? And then once we consider the feature, we get the extra term that actually come with this one. This is the cross term, right? This is not this is like an evidence, like that actually this new kind of feature that we have possess the non-additivity, right? Except for the first one in the hierarchy, for the q equal to 0, right? It means that for q equal to 0, you get the standard feature, then you get the additive property. That this is the reason why this q is called the solid index, something like that. Okay. Okay. So so far we have this. Okay, this one parameter here. Oh, actually, the parameter q in that inequality, but with the q here is different. They are different. This is like the q there should be the lambda here, something like that. Sorry for this mistake. Okay, don't be confused. Anyway, so with this one parameter feature, I can extend to the case of two parameter right away by just replace the standard exponential function by the q exponential function here. I get the two parameter feature information right away. And I would like to note that actually this two parameter feature information is different from what we have from the generalized Kullback-Leibler divergence. Okay, they are different. They're not the same anyway. But well, I just do that. Okay. So now we move to the case that actually we have multiple estimating parameters. We're going to have the feature metric here. And then for this case, we just propose that actually this is going to be our one parameter feature Rao metric here, taking to be this form, come with the parameter lambda. And again, if you expand this new feature Rao metric with respect to lambda, you will get the hierarchy of the matrices or the matrices here. And the first one is nothing but the standard feature metric. Okay. Okay. And so for simplicity, okay, we're going to consider in the case to estimate parameter, right? And then in the case of we have only two parameters in the system, the feature information, the standard feature information going to be this form. Okay, this kind of two by two matrix. And then if you expand this this whole thing with respect to lambda parameter, you will get the hierarchy again, but this whole hierarchy will be two by two matrices, right? The first one is nothing but the standard feature, right? And the second one is the new thing. And then this is what we want to understand what is this new thing is about to do with, okay, with physics or with math, that what we want to understand. So to understand the meaning of this this kind of new metric here, we're going to use this normal distribution as a prime example. With this normal distribution, the plot manifold, the manifold that actually associated with this normal distribution is nothing but the two-dimensional sheet, right? But with the upper plane, because the sigma must be positive, right? Sigma squared, right? then you get this kind of manifold here, and then once you use this plot to compute the standard feature, you will get this metric, and then you can treat this metric as a metric, right? Okay, that actually equipped on this manifold, and then once you get this metric here, you can write out the line element relation here. Once you get this relation, you can, for simplicity, you can redefine x1, x2 to be nu and sigma, and then I redefine again to be x and y. And by doing this, I'm going to get Gij and Gij, okay, the inverse of it in this way. And the line element can be put in this way, okay? So, if we have 2 points, as I mentioned, if we have 2 points here, suppose this is called P and Q, right? And if you want to find a distance between these 2 points, we just do the integration right here, along from the point P to the point Q, and the term inside is nothing but the Lagrangian in this way. And then you put this Lagrangian to the Euler equation, you will get this equation that we call geodesic equation, right? And then once you solve it, you will get the solution. And then if you look at this solution carefully, this is nothing that gives you the circle, right, equation here. Because if you square both sides, you get y square. It's something to do with the x square, right? You get this kind of circle. But since we have the condition on the manifold, actually the upper half plane for the sigma axis, right? We have the semi-arc of the circle here, right here. And then when you do plot, you will get this kind of curve, okay? That we call, we know that actually this kind of curve we call Poincare half plane, okay? And then, and if we have the point theta and theta prime, this is the shortest distance between these 2 points on this manifold, that kind of thing, okay? Okay, and so actually, what I didn't say actually there is a factor 2 here, but once I did this, I take out the factor 2 to make it simple, right? And then you get the circle here, the semicircle. But if you put the factor 2 back, you will get the half ellipse. That's it, nothing else, okay? And you get the same, okay? And so once we have the manifold, and then we have the geodesic equation. You can also compute the curvature of that manifold, and then we go through this the computation like a Tah symbol, Riemann curvature tensor, and then this kind of thing, and also Ricci this kind of what is called Ricci scalar, right? And then at the end, we find that this manifold, the curvature is negative 1/2. This is like evidence that actually this manifold is a hyperbolic space, right? Because there is a negative curvature, constant negative curvature, okay? Uniform as well, because it's constant. Okay, this is what we have from the standard feature information for this simple normal distribution here in terms of geometry, okay, on the plot manifold, okay. Next, we're going to see what we could have from the second function then in the hierarchy, right, I2 here. So once we compute the I2 in the second, this is the second function in the hierarchy, we get this kind of metric, and then I treat again, this is as a new metric that's called G tilde here. Once I have this new metric, I again write out the line element, and then I can solve for the geodesic equation for this relation, and then I find out that actually we have this kind of solution in terms of the hypergeometric function, okay, And we can do the same by compute the whole Christopher symbol or the Riemann curvature tensor, and then at the end we found out that actually the curvature of this manifold for this situation is not constant, right? Because it depends on the y variable, but the y variable is nothing but the sigma, right? Yeah. Okay. Then what we have is that actually on a very same space, if you equip this space with different metric, so the behavior of the geometry on that manifold is totally different, something like that. Okay, that's what we have. And so, well, let's come to the conclusion. So now we kind of success to, well, construct the one parameter feature information feature metric actually, or Fisher-Lau metric, but for the case of one random variable, okay. And then, well, there is somehow that what I mean by this two arrow here is mean that there is a connection with this solid entropy. There's some kind of share the same property that I call non-additivity, right? That is the reason why I use this kind of arrow here. Okay. Okay. So, well, let me give you summary. In the case of one random variable, we successfully. Oops, sorry. What? Okay. We construct one parameter generalized matrix by employing connection between principal and the multiplicative Lagrangian. That the way that we did, right? Okay. And we can construct the extension or the generalized Cramér-Rao inequality as well. Okay. And then this one parameter generalized feature information possesses a non-additive property, since we have q parameter in it, or the lambda parameter, you could say that. For the two parameter generalized, it also obtained, as I mentioned, you can just replace it with the q version of the exponential function. Okay. So, well, this idea can be extended to the case of many random variables. Okay. And the last point is that about the application, we don't really not yet about application because, well, it is still the open problem. But there is one interesting connection between information theory and the general relativity, because there is a paper in this one. Actually, they can construct Einstein equation from Fisher metric here. It means that there is a connection between you have the pop manifold here. Somehow you can build up the Einstein equation here, right, from the standard Fisher metric. So what I'm thinking is that now we have the one parameter version of the Fisher metric. We can maybe try to do the same process, and then we might expect to have one parameter Einstein equation. Well, I don't know. That what I expect, but I don't know. And this one parameter Einstein equation might give you more information about physics that we don't understand yet now. I think. Okay. Well, that's all. Thank you very much. Okay.
Okay, thank you for a very nice talk. And if you guys in this room have any question, it's about time to ask.
Just wondering if the Q plus associative. I mean the q-deformed plus is it associative?
Q.
I mean the very first slide where you define the q-deformed plus minus times and so on.
Oops, let me. Okay. You mean this one?
Yeah, maybe the next slide where you have the Q. Yes. Is it like the first one is it associative?
Oh, okay. Well, I actually I don't know. I haven't checked that, but I guess it should be yes. But yeah.
Yeah, I mean, I'm just simply curious whether they have the similar properties as the plus minus arms that we know.
Yeah.
How far they
Yes.
contain.
Yeah. I don't know. I haven't checked. Well, I haven't checked that, but I guess it should be. I think. Well, I will look on the internet.
So the next question is about the Salis entropy formula where you write in terms of the q-deform.
This one. Right?
Yes. So you use q-deform log, but I'm just wondering why not the sum is the q-deform as well. Why sum is the? I mean, why is summation the standard sum?
Oh, this one, right?
Yes.
Well, if you look here is okay. You have to take this factor inside. Well, I don't know. And we get back to the definition of exponential here, which is actually this one. Oh no, this one actually, this log here, right? I think you will get that exactly the same, right? Isn't it? If you take the 1 over 1 minus q inside bracket, and you leave the sum outside, you get this kind of log q x here inside that bracket. I guess that is the reason why you have the summation outside. Why is it in this way? And so.
Yeah. Just simply curious what would happen if you use a q-deform sum as well.
What was it? The q-deformed sum.
Yes, I mean because the summation is plus, right? You plus. You use the plus, right? But what if you use the q-deformed version of the plus instead?
You mean this one?
Yes, that one. Just simply curious.
I don't know actually. Actually, I don't know.
Okay, thank you.
Interesting. Yeah, thank you.
Okay, there is a question from the audience online. He asks that what would be an interesting problem that can be concisely solved via this nice new formulation of yours, such as proof of convergence of certain learning algorithms, such as expectation maximization. Or maybe would you like to?
Okay, I get the question, but I have no idea about the answer actually. Sorry for this. And I know who is who asked it the question. I can guess. Well, I don't know actually. Well, because this is still pretty new thing for me as well. And as I mentioned, further investigation is still on the way. So, well, a lot of things can be explored. I don't know. I don't know for that question about that kind of thing. Sorry about that.
So maybe was the same question that I asked you last day of the talk. I
Okay.
don't remember.
Yeah.
So does your new Cramér-Rao bow allows you to bow basically higher moments
Oh,
of the estimator?
yeah, I haven't.
If you go back to
I haven't checked that yet. You mean this?
oh yeah, so this equation, right?
Yeah.
Yeah, so below in the denominator is some weird power of the variance, and then what is the capital Q? Sorry, the capital Q 5/4.
Capital Q is this one.
Okay, so it's something that you can compute as well.
Yes.
So I guess it's sort of give you some way to bow this like weird power of moments.
Moment, right?
Yeah, I don't know what to call it.
Yeah.
For third power and then take average
Yeah,
and take the third
yeah,
power.
yeah. Well, I don't know. Yeah. Interesting. But actually, we did study the example for the normal distribution. What the second term here? What the expression for the second term here, and it's come out to be like in the second moment that you mentioned, something to do with the second moment, doing that kind of thing. And I believe that the second moment there is a very specific name for it, right? It's called kurtosis, something.
Oh, so it's like higher cumulant.
Yeah, something like that. Yeah, cumulant.
I see.
Okay, and then that kind of something to do with that kind of thing, and then we interpret that actually this give us when the way that we use this second function to estimate the parameter, we have to look at the tail of the distribution rather to look at the variance, something like that. That's what we interpret. Yeah. But I don't know what to do with this. Okay.
Thank you. Another curiosity. So presumably you can do all this business with quantum Fisher information too. Right?
I don't know, but I guess we can extend the idea to the quantum case.
So that would be like a new arena that you can perhaps find some applications of meaning.
Okay. So what it look like for the quantum version picture? Is it the same formula here?
I think it's sort of the same, but basically it would instead measure distance between operators. Like the state operators. So in the end, you would calculate some number, but there's something that you have to do there. To take the derivative of a matrix or something.
Okay. So the meaning of it is, it's quite similar, the same, right? Because now you can use it to be like a measure a distance, the difference between this. Yeah. Okay. I see. I will have a look. Okay.
We can talk.
Okay. Yeah. Very interesting.
Okay, if there are any questions. Okay, if not, I personally have one question.
No. Sorry. Okay, kidding. Okay.
I'm intriguing with like formulation of the Fisher information in the context of classical mechanics.
Okay.
Like if it's possible to like construct the duality, like some conjecture between these two theories. Like for example, you have like the information or the Fisher information term as the action, and probably the y as the time coordinate.
Mm-hmm.
Yeah, if it's possible to like having this kind of more conjecture, like momentum in classical mechanics can be interpreted in whatever in information theory and so on. I don't know. It just
I don't know. That would be interesting idea to investigate. I haven't looked at that yet in that direction, but I think we could build up that kind of dictionary. It's possible. I don't know. It might be not, but I think it's possible to do that. But so far we haven't done that. It's very interesting. Thank you for this.
okay. Thank you. If we don't have any further question, I think it's about time to say thank you for our speaker.
Okay. Thank you very much.
And I hope to see you guys in the next Tah Poe Seminar in next 2 weeks.
Okay.
In next 2 weeks, we will organize another one Tah Poe Seminar and
Colloquium.
and in colloquium and at the same day.
Okay.
Thank you.